This is example 6-2. We'll look at an airboat, right? So we have this boat right here with a big fan on the back, like maybe from the Everglades in Florida or something like that. And we are asked how much force this fan basically puts on this boat, right? How much would it accelerate based on that? So we're given how fast the air is moving out of the fan. We are given that the air around it is more or less has no velocity as the boat is going through it, but the boat is moving with 8 meters per second, right? So that gives us an idea. Now, if we're looking for forces, of course, we have to draw a free body diagram. In this case, we have something very simple, right? This would be the outflow. And we have some kind of where the inflow is, like this. Well, we'll say maybe inflow is here at A, outflow is there at B, and then we'll have, obviously, we exert only a horizontal force, so let's put F in there. I think that's really all we need for our free body diagram, but we can put ourselves a little coordinate system. In this case, the y direction doesn't make a huge amount of sense, but because there's nothing there in the y direction. But what are we going to do? Well, let's figure out some stuff. Right? We know that we're going to use the linear momentum equation, so we have to think about what the different velocities are. Very importantly here is that, of course, our boat is moving, so that means our control volume is moving. So we have to take that into account, especially for the flow of air that's coming in, right? Because it's not zero, it's moving with 8 meters per second. Let's get the flow through the fan first. So, oops, go back to blue. Small blue. So we can say flow through fan. Well, we know it's coming out at 40 meters per second, and we know the diameter, so we can just say Q is equal to VB times AB is equal to 40 meters per second times pi over 4. Diameter is 1.25 meters. And that's squared. That gives us 49.0874 cubic meters per second. Right? That's the flow of air coming out of our fan. Of course, means it also has to be the flow of air that's coming into our fan, right? Because we're not creating any air inside of the fan. Now, the other thing that we want to find is the velocity of air coming into our control volume, right? Again, we have two control surfaces. We have a control surface here, and we have a control surface there. Right? So how fast is the air coming into that control or through that control surface? It says that the air is at rest, but the boat is moving at 8 meters per second, right? So we can say, let's write that down, air at rest, but boat moving. All right, so we get our VA is equal to 8 meters per second. All right, that are the preliminaries. So we can now go ahead and write our linear momentum equation. Linear momentum equation. And we'll write the full one, and then we'll see what we can simplify. So we'll have the sum of forces, which is a vector, is equal to d dt of integral over the control volume of the velocity times density, which is a vector, times the change in the volume, plus integral over the control surfaces of the velocity times the density times the velocity dotted with the area. Now, in the case that we have here, what can we say? Well, we can say it's steady flow, right? There's no, boat is not getting faster or slower, so we can say steady flow. We are given a density for the air, which means the density is constant, so it's incompressible. Air also has very little, very low viscosity, so we can like that. So we can say that would be an ideal fluid, right? Incompressible and inviscid. And we can also say that we're going to use uniform velocity profiles. Velocity profile. So with those three, we can simplify our equation, right? So we still have sum of forces on the one side, but we know for steady and incompressible, we get rid of that first term, right? The control volume term drops out, and then we can write the rest here as just a sum instead of an integral, right? So we'd have, in this case, V times rho times V dotted with A, right? That would be our new equation. How does that relate to our specific case? If we look at our control surfaces, right? We have two control surfaces, A and B. We have control surfaces, they will have associated areas, right? We have an area there, an area vector there. At A, the velocity is going inward, so they're opposite, and at B, they're the same. So we can rewrite that down here as saying at VA, right, times our density, but we know this is negative, so AA times VA, that would be our dot product that we get. And then on the other hand, we get VB times rho, and now AB times VB. This is positive, right? Because again, these are aligned, the directions are aligned. So we can now take our vector equation and write that in just the x direction. So we'd have sum of forces in the x direction is equal to, now if we look at the velocity at A, the velocity at A is going opposite of our x coordinate, so that would be negative. So we'd have minus VA times rho times minus AA times VA. And then back here, B, the velocity also goes opposite to x, so it will also be minus VB times rho times AB times BB. Now we know that AB times VB, right? That's the Q that we calculated. We also said that the same Q is coming in, so we can rewrite that both as Q's. So we can say we take that negative sign here and the negative sign there cancel out, so we'd have VA times rho times Q. There we leave the VB times rho times Q, which means we can pull out the rho and the Q, and then we're left with the VA minus VB. Minus VB, and of course all of this has to be equal to the sum of the forces, right? So what forces do we have? We only have F. It's acting in the negative x direction, so all this is equal to minus F. So we can say F is then just the negative of that, right? So that would be minus rho was given to us in air 1.22. 1.22 kilogram per cubic meters. The flow we calculated to be 49.0874 cubic meters per second, and then our velocities, V at A, we said was 8 meters per second, and V at B was the 40 meters per second. So that is then 1,916.37 newtons, or 1.92 kilonewton. Right, and with that, we've used the linear momentum equation for a case where we have a controlled volume that's moving to figure out the force that this flow is enacting, in this case on the boat.